Morning, guys. So I'm going to be going over how to do three-phase power supplies when we look at having a word problem. So I've wrote one out here. We have a Y-connected three-phase power supply, outputs 208 volts. It is supplying three loads. The first is a delta capacitive load that sees 4 ohms per phase. The second is a delta resistive load with 6 ohms per phase. And the last is a Y-connected inductive load with 8 ohms per phase. So just going to start out with this one and say that we are going to solve for everything on the test when we end up having it next week. I'll ask individual things about what the total overall power is, what's the phase current going to be in the capacitive load, and then also perhaps what the power factor is of the circuit. Just off to the side, I've wrote down the key information that we have. We have supply of 208 volts, delta supply that's capacitive of 4 ohms per phase, resistive 6 ohms per phase, and the inductive of 8 ohms per phase. I'm going to erase this as I end up going through the problem. So I'll let you copy that down, pause the video, and then we'll come back and work through it. I'm going to try with only having the small amount of space to break down each part of the equation, so I can do all the steps and then I'll erase them and then move forward with all of our information. So we know that our supply, which was in Y, our supply was in Y. So if we have a 208 volts in Y, we know that our line voltage, so as we come out into the line, so if I draw that out, we have a line voltage. So if it supplies 208 volts, that means that it's 208 volts per line. Okay, so if it's 208 volts per line, that means that both of these coils produce a voltage that's going to end up giving us our 208 volts. So that means that it has to be root 3 smaller. So 208 volts divided by root 3 gives us an answer of 120 volts per phase. So we've got a supply that has 120 volts, so an E phase of 120, and our E line is 208 volts. All right, so we'll erase that. Now we get to our first load. Our first load is a capacitive load that is 4 ohms per phase. We know that we have a line voltage of 208 volts, and in delta, if the line voltage is 208, we know that there's only one load that uses that up, so our line voltage and our phase voltage are the same. So our E phase is also 208 volts. So our load 1 is going to have a E phase of 208 volts, a resistive, if you can see that, of 4 ohms, and then now we're going to look at what our I phase is going to be. So we have 208 volts. We look at I phase. I phase, we know volts divided by resistance gives us current. So 208 volts divided by 4 ohms, that gives our I phase of 52 amps. So 208 divided by 4 should be 52. So we get an I phase of 52 amps. While we have this up here, let's find out what our VARs is going to be, capacitive VARs, which is our reactive power from this, and we know that that formula is E phase times I phase times 3. So we take our 208 volts times 52 amps times 3. I'm just pulling this out here. And we have now 208 times 52 times 3. That gives us a value of 32.448 kVARs, and that is capacitive. So it's 32.448 kVARs capacitive, and I'm just going to put this down over on the side so that we have our power of load 2 of 32.448 kVARs, and that is capacitive. All right, so let's move on from this one. I already saw that information. Now we're going to move over to our resistive load. Our resistive load is also in delta. We have 6 ohms per phase, so we know that load number 2 is going to be our resistive load, and we know that we had a line voltage of 208 volts. So we have, 208 volts is our E line, and in delta, our phase and line voltage are the same. So we know that our E phase is 208 volts. 208 volts, if I want to find I phase, is 208 volts divided by 6 ohms. So 208 divided by 6 gives us a I phase of 34.66, around 7 amps. So I phase here is 34.667. And now let's calculate out what our true power is, our watts. Power is equal to, and we know it's just the same as last, E phase times I phase times 3. So 208 volts times 34.667 amps times 3. So times 208 times 3 gives us a total wattage of 21.632 kilowatts, and we can put that down here. So resistor value we knew was 6 ohms, and our power is 21.632 kilowatts. Excellent. Let's move on to the final load. Our final load is a inductive Y load. And obviously you'll have all the information on yours. I'm trying to do it this way just so I have a little more room and it doesn't get quite as crowded on the page. We knew that we, again, 208 volts for our line voltage, which means that we're root 3 smaller, so divide by root 3 or divide by 1.732 to give us 120 volts per phase. So load 3, E phase is equal to 120 volts. We have 8 ohms per phase, so if we want to find our I phase, we take 120 volts divided by 8 ohms, and 120 divided by 8 gives us a current of 15 amps. So we had a resistance of 8 ohms, and I phase is equal to 15 amps. And if we want to find our overall inductive current, or sorry, our inductive power, our VARs, we know that we do our E phase times I phase times 3, so we get 120 times 15 times 3, and that gives us a power of 5.4. So we have 5.4 kVARs inductive for our 3-phase. Remember, these are 3-phase because we're multiplying by 3. 3-phase inductive power is 5.4 kVARs. If you can't see down that far, I just wrote down the 5.4 kVARs in that spot. That was it. So we've got all the information written down. We found out all the powers for each. Now we're going to calculate our main supply values, so our 3-phase power. Our resistor values for our power, we know that it is, so that would be our load number 2. Load number 2, our true power, which is along the bottom, is 21.632 kilowatts. Our capacitive power is the largest of the two, so we know that it's going to be going upwards. And to calculate that out, we get our net reactive power, which would be 32 point, oh, we're in the glare from the light. I'll bring it down below. 32.448 kVars. Subtract 5.4 kVars, and that should give us an answer of 27.048 kVars. So that 27.048 kVars is going to go along the side. So 27.048 kVars, and that's capacitive as our net value. And once we have those values, we need to find out what our hypotenuse is. And this is going to be our apparent power, because there's a reactive and a resistive power involved. So we do Pythagorean theorem. So our a squared plus b squared equals c squared. So our c is going to equal to the square root of 21.632 kilowatts squared plus 27.048. Okay, I'm running out, I won't write the bars in, squared. So if you pound that out on the calculator, we have 21,632 squared plus 27,048 squared, and then just gonna write this down. So we have very large number, and my phone's being a pain in the butt right now to do this out, so let's do 11,995,3,7,728. We're going to take the square root of that, so square root should I have my calculator here for this rather than using the old phone. And we get a value of, should have 34.634 kVA as our total value. So we can write that over here. So our apparent power is equal to 34.634 kVA. And I know from the last video, you guys really liked moving between the two triangles to look at what your line current is. So I think I will do that with this one. So if I make this a tad bit smaller, I think you'll still be able to see it. So 27.048. Hopefully you can see that. 21.632. was our power triangle, and we have our current triangle over here. And remember I said that it was the line voltage. So our line voltage was 208, and then we times that by a value of root 3, because we're using line values, not phase values. So if we do it that way, we take our supply power divided by 208 times root 3 in order to get what our total power is of our line current. So if we do that and we divide by 208 times 1.732 or root 3, we get a line current of, could that work? Quite possibly. I'll check in a second. Of 96.137 amps. Now, so we're looking at line current for our resistive load. So we're going to divide by 208 times root 3. We get a value of 60.046. So 60.046 amps. And we now take 27.048 kVARs divided by 208 times root 3. So 27.048 divided by 208 times root 3, and we get an answer of 75.08 amps. And those, remember, as we said, were all line current values. So we have 96.137 amps, 75.08 amps, and 60.046 amps. So those would be all the line values. So this here, the 96 amps, so our I line from our power supply is going to be 96.137 amps. And if we now take this information, I'm going to take this off. So I'm going to write over here, our total I line is 96.137 amps. If I erase all that, and we come back to our supply. Our supply is in Y. It's a line value of 96.137 amps. And if we were to take an amp clamp and go on there, we see that it's only one coil that makes up, or one phase that makes up that 96.137 amps. And in Y, our I line and I phase are the same, so we also know that our phase voltage or phase current is also 36.137 amps. And just to check, we know that our supply voltage is 120. If we multiply that by 3, we should get the same total apparent power. So 96.137 times 120 times 3 gives us roughly, just a little bit of rounding throughout, but it's 34,609 or 34.609, so that is close. So those are the values that you're going to have. And then the last thing I want to calculate is our power factor. And power factor, if you recall, is true power over apparent power, or watts over VA. So our true over apparent power, so we have our true power of 21.632 kilowatts divided by our apparent power of 34.634 kVA. We are looking at a power factor of 0.62. Yeah, we rounded it just 0.62. It's 625 if you went to 3 decimals, or if we did it, yeah, let's do that, 6246, or a power factor of 62.46%. So that's how you would solve that word problem all the way through. Okay, I'll let you pause that, write that down, and we will put another question up. Okay, so I'm just going to write this out here quick, and then I'll give you a chance. I'll move it out of the way so you can copy it down. did it backwards. I just do them all at 6 volts. I was trying to do something a little different, but it would just make things too confusing. Okay. And we'll have our supply in, let's do delta. Okay. I was going to have it, and I'll just bring that up a little bit. I was going to have it where you're going to calculate out your main power supply, but I ended up listing them as, just so I didn't confuse you, those are all your line values of 600 volts. So yes, the voltage supply is 600 volts. I was going to get you to work backwards, but would have made it too confusing to change it to phase values. So I've got 3 loads are connected to a supply. The supply is in delta. Excuse me, load number 1 is delta connected resistive load. I see 600 volts in the line. Load 2 is Y connected and it's inductive at 600 volts. Load 3 is connected capacitive load, 600 volts. And we are going to do all loads are 8 ohms per phase. So my resistive is 8 ohms, inductive 8 ohms, and capacitive is 8 ohms. So this one I'm making it a little easier just because of I want you guys to go through it, but you will see things do take a change. Obviously, once you get into a Y connected load over the delta. So we're going to move all of our information over here. So the supply, we have a supply. Supply is 600 volts per line. Load 1, delta resistive. And 8 ohms. Load 2 is Y connected inductive. 8 ohms. Load 3 is capacitive. And 8 ohms. Okay, so I'm going to erase all this and then start going through it. So if you want, pause for a second and try and draw it out and go through it, and come back and we will go through this. So load number 1, let's start with it. It is resistive. In delta, and we have 8 ohms per phase. And we knew that we had a supply voltage of 600 volts. And if we have 600 volts in the line, that means we also have 600 volts per phase. So E phase is equal to 600 volts. Our resistance is 8 ohms. And 600, if we do, our current should be 125, I believe. Our I phase, so volts divided by ohms. 600 volts divided by 8 ohms, just so I don't make the mistake of 75, that's why. You do it on the calculator. So we have 75 amps as our total power per phase. 600 volts divided by 8, 75. Let's find out what our three-phase power is going to be. So this value's going to be in watts because it is a resistor. And so the formula, as you remember, is your phase voltage times phase current times 3. 600 volts times 75 times 3. So we have 135 kilowatts. Three-phase power, 135 kilowatts. All right. Load number 2. Is a Y connected inductive load. So we knew we had 600 volts for our line voltage and 8 ohms per phase. So resistance is 8 ohms. If we have 600 volts per phase and we go to come down into the line, we know that there are 2 coils or 2 loads that are going to be inductive loads that are going to be seeing that 600 volts. And rather than just writing 347, I will write the actual amount. So 600 divided by root 3 gives us a phase voltage of 346.42. So that is the voltage, our E phase, 346.42 volts. And now I want to find my I phase. So 346.42 divided by 8. And that was in volts. Divided by 8 ohms. That gives us a current of 43.303 amps. And now let's find our three-phase inductive power, which is going to be in bars. Three-phase power, and it'll be our volts per phase times our current per phase times 3. So 346.42 times 43.303 times 3. I know that's kind of getting off the board there. But 346.42 times 43.303 times 3. And we get 42.003 kVARs. That gives us 45.003 kVARs. And that is inductive. So we can write that down at the bottom. Just put that down a little bit so you can see that. Take that out so you can't see any of that. And then we had 75 amps here for our I phase. 75 amps. I guess without being on the Zoom call, kind of hard for you guys to say you can't see it. So that's that. So that's load 1 and 2. I'm going to look at load number 3. So load number 3 is capacitive. Again, 8 ohms per phase. Line voltage of 600 volts. We know that in delta our line voltage and phase voltage are the same. So load 3, E phase is equal to 600 volts. So let's do that. Yeah, 600 volts. So I phase is going to be 600 volts divided by 8, and what we figured out last time with the first load, that it's 75 amps. And I'm sure you can see where this is going with the ohmic values being the same. So if our ohmic values are the same, that means, and the voltages are the same, then that means that the powers are all the same. So we know that our 3-phase power is going to be 135 kilowatts capacitive. Or kilobars, sorry, capacitive. And just to make sure everything is, I didn't screw things up earlier. Yeah, 135. 3-phase power is 135 kVARs. So one thing is once we go over to our total values, how is that going to look for our power triangle? So our power triangle is going to look like this, just a straight line. So we take our, actually, yeah, the inductive was backwards. I don't know why did I do that? Yeah, so never mind, they won't be in unity, but those values will be the same because they're in delta, so that's right. We have a resistor value on the bottom, and that is 135 kilowatts. It would help if I wrote that was resistive, and that one was inductive, and that one was capacitive. And if we look at these, our capacitive value is much larger, so it's going to be capacitive again. I need to find our net power. Yeah, I need to stop doing these videos early in the morning, so I don't make potential blunders like that. 135 kilovars, subtract our 45.003 kVars inductive, that was capacitive, and we get a net value of just under 90. So that value, I'll write it over here, that value is 89.997 kVars. .997 kVars. That's capacitive, and we're going to do Pythagorean theorem here. Help too if the numbers weren't as big. Squared plus so we have a large number, but we end up getting a value of 162.248 volt amps as our total value for our overall power. And I think I have enough room to add the rest of it over with our triangle, our current triangle. I just draw the values in here on the inside for our inductive net current. So we are going to be looking at 600 volts as our line voltage. So 600 volts times √3. And that was, sorry, kVA. So divided by, so 162.248 divided by 600 times gives us a total line current of 156.13 amps. So I took 162.248 divided by this. So I divided by that. So that over that gave me that. Now we're going to do this over that to give you my resistive total current, our line current. us a value of 129.908 amps. And then now we're going to do 89.997 kVARs divided by this to get our net reactive current in the line. 89.997 divided by 600 times, and that gives us a net current of 86.602 amps. So that is our total line current. So I'm just gonna rate that. We got my line 156.13. Alright, so I'm gonna erase this now. Go back to our main power supply. You can see that I'll move back a little. So we knew that we had 600 volts per line, and our line or terminal current is going to be 156.13. So we have two coils that are vectorially adding together to get our 156.13 amps. So it means that our phase currents can be √3 smaller. 156.13 divided by 1.732 gives us a phase current of 90.144 amps. So we have a phase, I phase of that. We have a phase voltage of 600 volts because in delta our phase voltage and line voltage are the same, which was 600 volts. So we can also just verify our three-phase power this way too. So our three-phase power, which is going to be in volt amps, is going to be our I phase times 600 times 3, and it's around the same as the other, 162.259 kilovolt amps, and it was around that 162 value. If I go back here, yeah, it was 162.248, so we're very close to what it was. And now let's just calculate our true power here. How long is this video? We're about 55 minutes now. Power factor is our true power, over apparent power. So power factor is going to be equal to a true power, and our true power was, the first value, true power is 135 kilowatts. So 135 kilowatts divided by our apparent power of 162.259 kVA. total value of 83.2, so 0.832 as our power factor. So 0.832 as a power factor. And I hope doing it this way, I realize I am erasing a lot of what's on the board, but I'm hoping in doing it like this, where I write the question, move what's required over to the side, it really allows us to clear up a lot of the space so that it makes it easier to go through and do all the questions. I do realize that this is a lot to go through and take in. And as I've said before, and I'll reiterate it again, there are so many questions that I have online and in Dalmars to go through and to help with all this. And really, you know, being able to go through and, you know, the more you do of them, the easier it's going to be. So going through and being able to practice them, you know, every day, just do a little bit more of the questions to get you through into the test is going to help you out immensely. I'm just going to do a couple variation questions that you might be able to see on the test. So they won't take long to do, but it just gives you a slightly different spin on what the total is. So I'm going to write the question out, and then we'll take that information and solve the answer. Alright, so here's a different spin. These questions can go a little faster to go through, but gets you to use your brain in a slightly different way rather than just pounding out the whole long question. I've got a three-phase power supply, outputs a total power of 600 kVA at a power factor of 87%. What is the total true power in the circuit? So we're going to take out the important information. We know that we have 600 kVA and we have a power factor of 87%. Obviously we don't need any more information than that. You may find that I do end up having questions where I have the question that you see in the back, but I add, you know, a supply voltage of 347, and maybe add in efficiency or even current values, but obviously me adding in different stuff is just to distract you, and definitely it can make the question harder, but at the end of the day all this stuff is leading you towards writing your certificate of qualification. And once you get to that test, you're gonna find that every single question on there is meant to try and distract you from the right answer, which is unfortunate, but you know, at the end of the day, that's how it is, and that, I believe, over the last 3 years is what we've been trying to gear you towards. So if we can you know, make things a little harder now to make things slightly easier later on, or slightly more comfortable, then you know, that's you know, our overall goal for you guys coming here and going through and doing all this stuff, and why we put in the effort that we do. So so formula we need to go with is power factor is equal to true power over apparent power. And if you want to stop and work on this before you look at this, more welcome to do that. So we know that the power factor is 87%, which as a decimal is 0.87. True power is unknown. When we do questions like this, I find sometimes it's easier to put the values in rather than rearranging first. 600 kVA. And always when you want to isolate something, whatever you do to one side, you have to do to the other. So I'm going to multiply by 600 kVA on both sides just to get the division out of there. Multiply on this side by 600. And that leaves us with an equation of 600 kVA times 0.87. And something you're going to realize too with these questions is your true power is always going to be smaller than the apparent power at the end of the day. So in this case, it's 87% of 600 kVA. So 600 times 0.87 gives us a total true power of 522 kilowatts. If you look at what I have here, you could, anytime you have something that has 3 variables in it, I don't always like using it, but you can do it. You can put it in a triangle, right? Anything that's 3 values, you can put in a triangle, and I know some of you guys really like triangles. And if I were to do it this way, so obviously you guys remember the I is equal to, or E is equal to I times R, where we had the voltage and the current times the resistance. Well, we can do the exact same thing here, where we have our apparent power and our power factor down below and our true power up top. And if you want to flip those, that's fine too. So whatever you want to figure out, you just cover the item that you're trying to find. So if I'm trying to find true power, in this case it's apparent power times power factor, which we did here. If I'm trying to figure out power factor, right, it's true power over apparent power. Or if I'm trying to find apparent power, it's true power divided by power factor to make answer slightly larger. So if you want to use that and remember that or write that down on a test, you're welcome to. Only problem I find with doing it this way is as the year progresses, we're going to have questions that are more and more complicated, that have more and more variables to them, and you can't always put them in a triangle anymore. So if you can really understand cross multiplication and why we move things around the way we do, it'll allow you to get away from this, so you're not just stuck on a triangle, and is going to help you out a lot more, because a lot of guys too will even they'll make or even memorize all the different variations of a formula, and there could be 3 or 4 different variations of a formula when they have more variables. So they go into a test and they have 15 to 20 formulas all memorized, where it may only be 4 formulas, but you just need to learn or know how to manipulate them. So if you can learn how to manipulate a formula, it'll make your life quite a bit easier than just remembering a million different formulas. But that obviously does help as a aid for you. I'm going to do one more, and then I'm going to end this video. This one's fairly straightforward. I'll let you pause it and go through it. But a load that is resistive has a total 3-phase power of 7.2 kilowatts. The total circuit has a power factor of 93%. What is the apparent power of the circuit? So I take the important information. 7.2 kilowatts at 93% power factor. And as we said before, power factor is true power over apparent power. We have an apparent power of 0.93 and or 93%. We have a true power of 7.2 kilowatts, and we have a apparent power that is get all of this rearranged, so you can use the formula or the triangle if you want, or you can cross multiply. One easy trick with cross multiplication, if you have a parent power as the denominator, the bottom number, and you have a number that is over here, you can actually just swap the two values, and it'll allow you to find that unknown value, other than multiplying by the apparent power on this side and then the parent power on this side, and then dividing by 0.93 and then bringing the 0.93 over, which is going to take a fair bit of time. You can just do the old swap, but if you did want to know, multiply by apparent power here, multiply by apparent power over here, which is going to cancel out that and that. But once I do that, then I need to divide by 0.93 on this side, divide by 0.93 on this side, so the 9.3's cancel out. So just like I said, you can just swap the apparent power and the 0.93, so it does work. Just do the old swap. So 7.2 kilowatts divided by 0.93 gives us 7.74 as our apparent power. So 7.74 kVA as our apparent power. So that's everything in a nutshell. Please go through and do all the questions that I have for you. I believe you have enough information now to successfully rate the first test that we're going to have, and the lab classes that we're having are, reinforcing everything that I'm telling you, and yeah, so should be good. So enjoy the rest of your time. If I don't see you before the weekend, then yeah, have a good day.